Good morning to all you brave people who are here to start today's session. And we're delighted to have Alexander Goncharov here to tell us about a slightly modified title, Geometry of Canonical Bases and Mirror Study.
Thank you very much. Thank you very much to organizers for inviting me to this exciting meeting. So I'm very pleased to be here. So the title on the blackboard. So let me start with the main heroes. So what is the initial data? So I start with the data, topological data S, which will be a topological oriented surface for which I reserve notation just little s, plus some little data. So first of all, it could be with or without holes. And plus that, it has a collection of special points on the inside or on the boundary. So altogether, it looks like that. So first of all, you have a topological surface S. It may have cusps, which mean just punctures inside. And these are one of those special points. Let me just introduce a set of special points. But it also may have some special points on the boundary of holes. Actually, it's assumed that if there is a hole, there are special points there. Otherwise, the hole will be drawn as a puncture. And so it's pictured like that. Once again, inside I don't put special points, because if I put a special point, let's say somewhere here, this means immediately that I think about this as a puncture. Well, to be honest, there is a little bit more of data, so some of the special points, and quite often all of them, will be somehow marked boldface. You can assume all of them marked boldface, at least in the beginning. So that's the topological data. Now also, I need an input from Lie groups, so I have G, which is a split semi-simple algebraic group over Q. And for all practical purposes, you can assume that this group is SL2 almost all the time, because the story will be new in this case already. And sometimes it will be new only when you go to the groups other than that. So you can assume it's SLN if you don't want to go any higher. So that's the input. Now, what's the goal? So what I want to do, starting from this pair, G and S and G, I want to define a dual pair of modular spaces. Which are related to modular spaces of G-local systems. On S. Notice that here S is not this S, but just the surface. So I just want to reserve some notation. So one of them will be really the true analog of the set of the modular space of local systems on the original surface. But if we have these funny points, it will be somewhat different. And another one, just again, it's just a letter for it, called this way. This is some modular space which we're defining with folk about a decade ago. And the new point is that it will come with potential. There will be function on this moduli space, which I'm going to describe. And one of the connections, so I said they are dual, and one of the ways to express in what sense they are dual is the following. So I will define something which I'll call a set of W positive integral tropical points of this A space. And this set will parameterize canonical basis in the linear vector space of all regular functions on this generalized local system. So mind, here's the following very important feature, that these moduli spaces are dual, but one is both are defined using S, but one is defined using the Lagrange dual group, and the other is defined the usual group. Now, this bottom correspondence, the main proposal is that it's actually trace of a much deeper correspondence, which is a mirror symmetry. And so I'm going to explain basically this quadrilateral. OK, so let me start with an example. Let me explain an example of a canonical basis. So far, didn't say anything. So let's, and once again, whatever I'm going to say, first of all, I will specify S and I specify G, mostly S, it's important. And then we'll do something related to it. So what if you take example
W positive
tropical points.
tropical points.
Yeah, good. Tropical. And I'll do my best to explain what this is. But the most important point here that that we have some mirror symmetry pair related to group G and this decorated surface, which involves Lagrange duality. And most importantly, it involves Landau-Ginzburg potential on one of the sides, which is the main hero of the story because it wasn't considered before, even for SL2 in most of the cases. And then the same data, as I will explain, produce just a set, the set of tropical points cutted by the Landau-Ginzburg potential. And this set will be shown that it parameterizes canonical basis. And since I'm talking both to physicists and mathematicians, OK, let me make this comment later. So I'll
already known to be mirrored to something else, so how is it related?
No, not, I mean, OK, you said right-hand side is known, but I didn't even define the right-hand side. What is this?
Well, I mean, it's known to be mirrored to something.
What is log?
Local systems, no?
No. Now, Sergey, you said it's known. It's known probably in the case when you have a closed surface, right?
Well, even with punctures.
Huh?
Even with punctures, yeah.
OK, with the punctures, what's dual to?
Well, it would be dual. I mean, it's in the Hitchin moduli spaces.
OK, but now it will be with potential will be slightly different.
That's why I'm asking, is there a relation to that or no?
OK. Example. Let's suppose that G is SL2, and S is closed just for simplicity. It could be with punctures, but I just want to say precisely. Then, in this case, this log SL2S is just usual SL2 local systems on S. And the same happens, so just since Sergey asked, so whenever you put this S to be without just surface with punctures, it's going to be local systems usually, because still there are options, but you can think this way. So now there is a theorem which describes the canonical basis, which we proved with Fogg about a decade ago. So the whole point of this theorem is when it's closed or with puncture. I mean, it could be any S. So it's done for any S and SL2. But just for the purpose of simplicity, I'm going to explain what it means when it's closed, the simplest possible case. So this theorem says that the bottom correspondence is available. And it says that there exist a canonical base. Actually, it's a construction in the space of regular functions on this log, parameterized by integral laminations on S. And in this particular case I'm talking about, when it's closed, it's even the very classical, the Thurston's integral laminations. So my first, so I'm going to explain how this works. Not that I will prove this theorem in a second, but I'll just outline the construction. And in particular, I'm going to define what's lamination. So definition. So we have now a surface which has no punctures and no holes. And lamination, elimination, is just a collection of non-intersecting curves with multiplicities, which are not self-intersecting and simple. And they come with some multiplicities, n1, n2, n3, and non-isotopic. So you can write such elimination L as a linear combination, n1 times alpha 1 plus and so on plus, it's a formal sum, nk times alpha k. And these ni's are natural numbers in French or any other sense. I mean, it's a non-negative integer. And this alpha i's, this is just alpha 1, this is just alpha 2 and alpha 3. Let me say without writing, so they're loops, maybe write a little bit, simple loops, non-intersecting, moduli isotopy. So just data like that. So how we construct a function on the moduli space. So this is done as follows. And again, it's kind of a natural thing to do so. If you start with this L, you're going to assign a function. And so first of all, you want to decide what to do if you just have a single loop. In this case, you can take the monodromy of your local system around this loop Li, alpha I, sorry. If you have multiplicity, you better raise this monodromy to power ni. Then to get a number, you take a trace of this. And if you have many loops, you take a product when I goes from 1 to k. And of course, this procedure, when you take a loop and take trace of monodromy, this is something very, very, very well known. And it's very, very well known that if you take all these traces of monodromies for all loops and consider the algebra they generate, you get all functions on local systems. It's again very, very, very well known. The little novelty here, I mean, in general case, not only when it's closed, but also with punctures and so on, is that there is a special way to get a linear basis. Not basis as an algebra, but a linear basis. And then you really have to deal with laminations here. Now, I want to emphasize that that's a rather strange situation when you have a vector space, and this vector space has a basis, which is absolutely canonical, for example, invariant under the mapping class group, and does not depend on any choices. As far as I know, the first situation like that happened almost like that, when Lustig defined his canonical basis in finite dimensional representation, which was kind of shocked, because why representation should have a basis? In that case, it's almost canonical because it depends on the choice of Cartan subgroup in your Lie group. But in this case, it's totally canonical, even slightly better. And another thing is that, OK, it's a basis. Usually when we construct a basis, we parameterize by integers or by sets of integers, by something. Here it's parameterized by something funny. It's an object on its own, these laminations. And OK, and finally, talking to physicists, so there is something physicists call line defects or operators, I don't know. And this is actually it. So that's, if there will be no objection, I would say that this should look for physics audience as a kind of line operator. So you can propose, you can say that, OK, to define line operators for higher group, you just need to define this canonical basis. That's by definition what it's supposed to be. OK, so that's the story is about that, so to speak. Now let's go to the next example. And in this example, I will take S to be a disk with n special points on the boundary, but G will be arbitrary. And so the question is how you define canonical basis in this case and who is lock in this case. First of all, I need to give you a little background in Lie group. So first of all, there is a flag variety. I'm talking to students sitting there because I believe everybody knows this. There's a flag variety, is a set of all Borel subgroups. And then there is another thing which is projects to flag variety, which is slightly less popular, which is called principal affine space. Now, here, flag variety can be written not canonically if you choose a Borel subgroup as G mod B. This guy can be written not canonically if you choose Borel subgroup again as G mod U, where U is a maximal unipotent sitting in B. And so, obviously, by definition, you have a projection from here to here. Now, for example, if you take G to be SL2, then this A is just a two-dimensional vector space minus the origin. So just the set of all vectors, because this is SL2 mod unipotent group. Well, that sounds good, but it's actually not a good definition of, I mean, this is a definition, but that's not what I'm going to use. So let's suppose now that the group is adjoint. Assume that the center of the group G is trivial. Then there is an infinitely better definition of principal affine space. In this case, it can be defined as a moduli space of something. So in this case, you define A to be moduli space of pairs which consist of maximal unipotent subgroup U in your group G and a non-degenerate additive character from this unipotent group. So it's important that this is non-degenerate. Again, what it is if the group is SL2, what is a non-degenerate character? So you have a unipotent subgroup. Any of them is conjugated to this one. And a character of this can be constructed by taking a complex number lambda and associated to this lambda A. So now product goes to the sum. Non-degenerate means that this lambda is a non-zero number, and that's important. In a more general case, if you have SL3, then the unipotent subgroup is this, and the number will be lambda 1A plus lambda 2C, and this lambda 1, lambda 2 belongs to C star. That means non-degenerate. Non-degenerate means it's a Cartan group X, and you have only one orbit, and there's of the section. So this is C star to the rank. OK, why this is the same as before? Because the group G acts by conjugation on data like that. And if the center of G is trivial, there is no stabilizer. So you get an isomorphism. Notice that this is kind of misleading to say that this is G mod U, because when you say G mod U, you mean you have some point here, you know, the preferred point. But actually, this preferred point is not U. It's U with non-degenerate character. And you somehow, when you're talking G mod U, you forget about this. OK, you will see in a second why I spent so much time talking about this. Now let's define the space and the potential. Yes?
I would have thought that all of the U's would be equivalent.
What?
I would have thought that in this example, G would act transitively upon the U's.
Yes, definitely.
Information in kind.
This is, yes. So let's go, first of all, let's take not SL2, but PGL2. You consider the set of all of maximal unipotent subgroup. And this is identified with projective line, because any maximal unipotent subgroup sits in this normalizer, which is maximal solvable subgroup, which is conjugated to upper triangular. So it's projective line. Secondly, to any point on this projective line, you have C star points related to this, which is this non-degenerate character. So you have a bundle over P1 with a fiber C star. What this bundle is, this bundle is in coordinates C2 minus 0 projected to complex projective line, where you just take a vectors and you assign to these vectors the line which passes through this point. Now your next question would be, okay, take a vector, associate the character. Good exercise. So I'm just saying this is the same data, okay?
I'm just surprised that G doesn't act transitively on use.
G does act transitively on use, as you just said, because use forms CP1. So what's the problem?
The CP1 distinguishes different use.
Yes. It's not a quotient-based action of G. It's just a set of all U's and K's. Anyway, so yeah, good. Thank you for the question, because somehow this is the central topic, although this is the central point. And if you miss it, it's not good. So now let's define this lock. In this case, lock G, I call it disk in this case. Well, I better not write it down. Let me just introduce the space, because it will be the same. So let me introduce the space conf n A to be just the nth power of the principal affine space divided by G. So you can call it the space of configurations of n points in principal affine space. Now, this will be secretly my space A related to the group G and disk with n points. And remember, on the left-hand side. So this means that I need to produce a potential. Let me introduce here subspace conf n star A. So it's specified by the conditions that any pairs of affine flex in generic position. Let's see what it tells you in the case when you have SL2. So in the case when you have SL2, n points in the principal affine space just means that you have n vectors, v1, v2, non-zero vectors in a two-dimensional vector space. I write C2, but I mean, of course, this is a two-dimensional vector space with symplectic form. Now, they take in modulus the action of SL2. So we can write this like that. Now, if you take any pair of vectors, let me introduce notation. Delta ij is the area spanned by vi and vj. So you can just say this is this, I should introduce notation. This is a symplectic form elevated on vi, vj. Now, I'm going to assume that these areas here are non-zero, and this means that these vectors are in generic position. So no two neighboring vectors is going to be collinear. And there is a similar condition in this case, which stems from the fact that if you consider the space of pairs of points in this space in the generic position, it's actually isomorphic to Cartan group. And so this to be true, you have to put this generic position. It means that the underlying flex are in generic position, related by W0 as a Schubert cell. Now, we are going to construct a function which is the main hero, the potential in this case. So how you construct the potential? So let me do it here. Well, I start with the following observation, that if you have a set of pairs, A is a point of principal affine space, and B, which is a flag, so this belongs to the space of configurations of points on A and B, which is literally just A cross B divided by G. And if you assume that they're in generic position, it's obvious what it means now, then the space is a principal G space. It's kind of a space of frames in your space. Now, in example, the point of B means a line, and the point of A means vector. And I'm saying that if you have a vector and a line in generic position, that's a principal homogeneous space by SL2. Indeed, you can recover the second vector here so that the area is 1. And then you're talking about pairs of vectors. Vice versa, if you have a pair of vectors, you can consider one vector in the second line. So it's a principal space, principal G space. Now let's assume, and I draw again this picture, that you have a collection of points of A. So here you put A1, A2, A3, A4, and so on, AN. Let's take one vertex of this polygon. And so what do you see when you look at this vertex? I draw in a bigger scale. You see that you have here a fine flag or decorate flag, but you can put here BI. This is the underlying flag which corresponds to this. And here you can have AI minus 1 and AI plus 1, which are the points of the principal affine space which corresponds to this thing. So you just concentrate on this angle, so to speak. And then I'm going to say that there is a unique, in this case U3, element of the group which transport this frame to this frame. So in this picture, the claim is that there exists unique UI in the group G. So I picture this UI here, which has the property that when you consider this guy, and this guy is BI AI plus 1, and then you apply UI to this guy, you get the other guy, BI AI plus minus, it's minus plus 1. So that's a defined property. Again, this is like a frame. There exists unique vector, unique element of the group which moves one frame to the other frame, right? Now, I'm one step from defining the potential. The point is that remember that this A, which is point of G mod A, comes with a character. You remember that if you have any element A which sits in this principal affine space, you have the associated character chi A just by definition. So decorated flags knows the character of the corresponding unipotent group. And so you just define the value of this character chi AI on the element you produce UI, and you get a number. And now by definition, the potential W is defined as a sum over all vertices of these characters associated to decorated flag sitting at the ith vertex evaluated on the unique element which sits at this vertex. So we get a function, and this function is regular in this space by definition, because whenever you have generic collection of affine flags, this is generic, this is frame, it's well-defined element of the group, that's a character, you pair them, you get a number. That's my potential. Okay. Let's look on some examples how this little abstract definition works in some very concrete cases, SL2. So let's suppose that we have configuration of 3 vectors in 2-dimensional vector space, V1, V2, and V3. Then the potential, as always, is the sum of contributions at the edges, at the vertices. So I just need to tell you how to calculate, in this case, the potential here. And the answer is that this W1 is just delta 2, 3 divided by delta 1, 3 times delta 1, 2. These deltas are the areas of the corresponding pairs of vectors. And then you take the sum, and you will get something like this, delta, in this case, 1, 3 divided by delta 2, 3, delta 2, 1, plus delta, in that case, 1, 2 divided by delta 1, 3 and delta 2, 3. So this is the potential in the triangle. OK, now let's formulate the result. So the claim is that whenever you have a space, an I space with lots of coordinates, and that's the case here, so that the transition functions between the coordinates have no minuses, you can define something which is called the set of tropical points. So if you have some space X, any space, and function W, and this is something which is called positive space. Forgive me, I will give a definition in a minute, but just admit it as is. Then it produces you to a set, which I'll denote as X plus WZT. And this set is defined in 2 steps. So first of all, if you just have X, then this X provides you a set, X of ZT, of all integral tropical points. And the way you proceed, this set, let me describe it, is always isomorphic to z raised to the power dimension of your space. But this isomorphism is never canonical, because the input here is that you have a space and you have a lot of coordinate systems on this space. And for each of coordinate system, you create a collection of integers, which you call this tropical point. And when the coordinate system changes, you get some transformation rule. So let me explain this on example. Let's suppose that your space is assigned to 4 vectors in 2-dimensional vector space. Then there are 2 ways to introduce coordinates here. You can have this triangulation, or you can have this triangulation. And then you can put this delta, so you can put here delta 1, 2, delta 2, 3, delta 3, 4, delta 1, 4, and you can put here delta 1, 3. Well, actually, this is 2, 4. And the same picture here, except that you put here delta 1, 3. And the same other 4 numbers. And then there is a Pluke relation that the delta 1, 3 times delta 2, 4 is delta 1, 2, delta 3, 4 plus delta 1, 4, delta 2, 3. And now when you want to tropicalize, this is just description of set of configuration of 4 vectors and coordinates there. But if you want to tropicalize, you say that actually you just have collection of numbers assigned to these edges. And the transformation rule is the following. Let's call these numbers like delta. Delta 1, 3 plus delta 2, 4 equals maximum or minimum, I never remember. Delta 1, 2 plus delta 3, 4. And delta 1, 4 plus delta 2, 3. This is a process of tropicalization. So you downgrade the product to the sum to the maximum. Again, product goes to the sum. And now this was kind of functions. And now these deltas are just integers. And so by definition, a tropical point of this configuration of 4 vectors is a collection of all integers you can put on the diagonal. Model is a relation that whenever you have a relation for actual coordinates, you have to impose the tropicalization of this condition, which defines this way. I hope it's clear now how you, in principle, can define the set, right? Now, the point is that if you have a potential, then you can consider, you can cut this z to n to something which is just a convex polyhedron, usually or infinite polyhedron. So this x plus wzt is the set of all tropical points in x of zt, which has the property that the tropicalization of your function is non-negative. That's it. The set is defined. Now there is a theorem, and this is somehow the main point, that in our example, the set parameterizes in a natural way a canonical basis. So kind of one of the main theorems that the set conf n plus a for the group G, and I can put here zt to emphasize it's a set of some integers with some relations, it parameterizes a canonical basis. In where, now I have to tell you what the dual space is. And the dual space, in this case, is just exactly the same space, conf n, related to the Langland's dual group. And so you just take the set of the linear space of all regular functions on this space. So, Sergey, this is the answer to your question. This is a set of local systems on the disk, the right-hand side. You see that on the disk, you have no local system whatsoever, but the space is big. That's the space. OK, let's look what the theorem tells you in an example. So in this case, if you want to do, and the most basic case is when you have n equals 3, if you want to talk about tropical points, you put here 3 integers, lambda 1, lambda 2, and lambda 3. And this condition means that if you consider any of them, let's say lambda 3 minus lambda 1 minus lambda 2 is, as I put it, it's non-negative. I actually better put here, I mean, I just changed the signs, put it less, wait a second, yeah, less than or equal to 0, just changing the notation. And so this means triangular inequality, that the sum of these two integers is bigger than this integer. So this implies, if I put notations like that they are all non-negative integers, and sum of any two is bigger or equal than the third one. As everybody knows, that's exactly how you parameterize invariance in the product of three representations of SL2. If you have three finite-dimensional irreducible representation of SL2, then the space of invariance is either one-dimensional or two-dimensional. And it's one-dimensional, not two-dimensional, exactly when you have this triangle inequalities. And so in this case, it at least matches with what I claimed. Lambda is a good question, Nikita. So lambdas are integers. The tropical integer as a point of a set is an integer. The only difference between tropical integer and our integer is that arithmetic of tropical integers is different. And so here, it's a good question. So I want to consider the set of all tropical points of this conv 3 of vectors in V2. And then as a set, it's just z cube. It's given by a triple of integers, usual integers. Now I have the Landau-Ginzburg potential, this one. And what it does, it cuts among in this z cube a subset which is either consists 1 point or 0 or empty set. And the subsets, oh sorry, what I said is not what I mean. I mean just given by these triangular inequalities. That's what I mean. Because when you tropicalize, you get this minus, so this must, this minus this plus this has to be, as I put it, less or equal to 0. Okay? And then this is supposed to be true for all of them because you have to take maximum and still less or equal to 0. And now this is exactly the set which parameterizes invariance. And so the point is that the same is true in general for any group G, and actually.
So lambdas are just tropical scalar products of the vectors, right?
Yes, this lambda is a tropicalization of the area, symplectic area of pairs of vectors. Yes. But again, without potential, you are kind of dead because you don't see anything. So potential tells you that you have to have triangle inequality, and it singles out you some finite subset afterwards. I mean, in this case, it just said that if you label but these three integers, three finite dimensional representations, so you consider something like v lambda 1, tensor v lambda 2, tensor v lambda 3, and look at SL2 invariance here, the invariants are parameterized by those, exist only if this three lambda satisfies this triangle inequality.
Should I think about this as of actually approximation to something which actually takes place, like I'm studying some exponential integral?
Yes. This is you're going a little bit ahead of me. Now let's rewrite this theorem in a different way. So I explained what it means, but it turns out that you can just rethink what it means as follows. So you can reformulate this. This is just reformulation. That there exists canonical pairing and canonical pairing is a pairing between a space, and the space is the space of configurations of n vectors in principal affine space for the Langlands dual group. And the other set is the tropicalized configurations of n points in the principal affine space for the group G, tropicalized by using this potential. So somehow there's potential present here, and I take the tropical points. So this is a set. This is a set. And this is a space. And the claim is that there exists a canonical map, just single map from the set multiplied to the space to complex numbers. This is just a reformulation because it says that whenever you have a point here, you can think about this as a function on this space. And that's in particular what the theorem tells you. But you see, now the picture becomes kind of symmetric because you see the most important and miraculous thing here, you have the group G here and the Langlands dual group here. And so what you can say, okay, why don't we take configuration of n vectors in A, G, and multiply it by the set of tropical configurations of points in GL, ZT, and again get mapped to C, right? I just interchanged the group G with the Langlands dual group, and so the space here becomes is going to space here. And so it looks as follows situation. we actually do have, let me put it here. We have two spaces, one space here and another space here. And if we go to tropical points, and as Nikita was trying to hint to us, the tropical points really mean some kind of asymptotic behavior. The set of tropical points secretly lives as a set of discrete points on some kind of boundary, on sphere of the boundary of your original space. That's what it means. If you take the points on the boundary of one of the spaces, you can pair it with the points outside the other space. That's what the theorem tells you for the group G. If you go to the group GL, you do something different. You're saying that in this case, you can take the points inside of the first space, and you compare it to the points which lives on the boundary of the second space. And you still have a pairing. Now it's very tempting to say that these both effects are actually traces of something deeper which is going on, and that's the mirror conjecture. So now the conjecture that there is a mirror symmetry relating these two spaces between conv and A for the group G and conv and A for the Langlands dual group. All right, now let's try to play a little bit with this statement and see what it gives us in some other cases. Oh, yes, thank you very much, then. That's very important. So in particular, I mean, to say this mirror, I really have to put here the potential to one of them. And then this guy has mirror dual to the other end. So in this case, I consider generic points. In this case, I consider all points. So let's cook up some data which we can observe, so to speak, which corresponds to the left-hand side. And so you can write, so first of all, this space has natural volume form. It's kind of D-log volume form, which I denoted by omega. That's a general property of all the spaces as it follows from its description as cluster guys. And what you can do also, there is here map, so this conv n A maps to a torus, to the Cartan group raised to power n. And also there is an action of the Cartan group raised to power n on this space. This is actually the data. So you have the volume form. Okay, let me just put it this way. So one group X, one group, and you project to the other group. Now actually, if you consider the dual space, it will be a similar picture, but now the tori will be Langlands dual tori. And now the mirror duality tells you that actually these pictures are interchanged so that the projection becomes the action, and the action becomes projection in particular. But there is one particular thing which you can do just with this projection. Let's call it pi. Let's write down the integral which corresponds to this. So what you can do, maybe I do it here. You can use potential in the usual way to write down the integral. So just writing down integral of e to minus this potential with respect to the volume form, which you have on this space. And you integrate over the fibers of this projection pi. So in the end of the day, you get a function which depends on n elements of the Cartan group. Now, I should say actually how you integrate. The point is that this space is a positive space. And so here there is a subset, a kind of positive cycle. This is a subset in this configuration space, which consists of collections of affine flags, where again I fixed if for SL2 I fix this boundary values of areas, but then I have these two free parameters here. And the nice thing is that you can assume that now these coordinates are real, and not only real, but real positive. And this states, if you change the triangulation, still will be real positive. So there's a beautiful cycle which consists of really positive, real positive part of this subspace with given boundary data. Now you have e2 minus of a positive function evaluated in this positive space. It has a good chance to converge because this is e2 negative number. It can only diverge if this is 0, but in this case it's convergent. And this defines a function. Now, in particular, one of the mirror conjecture has many different flavors, and of course the main flavor of mirror conjecture is a homological mirror symmetry. But you can have something more visible than that. I mean, something in your hands. You can say just that this function solves the system of quantum differential equations which you see on the other side, where you take into account the action of this group here. So you really then would need to take GIT factors of n affine flags here, modulus the action of this group here and the group G, and then you can something where you can try to calculate the quantum cohomology, the small quantum cohomology, and it will live exactly on this space, because it will live basically on the character of this space, and this story is a Langlands dual. And so this is one of the concrete ways you can formulate this. You can say, okay, this function solves the system of differential equations. Then you can ask, okay, do we know anything like that which can immediately justify this claim? And the answer is yes, that if you consider, and this is probably the last thing I'm going to say, unfortunately, that if you consider a slightly different example. So again, as I said, you can play with a triangle, and you can consider three elements of the principal affine space related to this triangle. And from the point of representation theory, we're talking about the invariance in the triple tensor products. And from the point of view of mirror symmetry, we're talking about this function. And remember that I choose the potentials to be at the three vertices. And the next simple thing I can do, I can take the same triangle and put here potentials only here. So I put here A1 and A2. And as soon as I do it, I better put the flag variety here, B3. So that's a different configuration space. And I better assume that they're in generic position here, just a technical, this is an important assumption. Then the theorem tells you that this is canonical basis parameterizing vectors in the finite dimensional representation V lambda of weight mu. So you have this classical problem here, then you have this classical problem here. Then you say, okay, why don't you go to the bottom and consider the same triangle and put just one boldface point, which means you put a affine flag here and two flags here, B2, B3, and play the same game. Again, as soon as I put these boldface points, you know the potential, because the potential always works this way. So here's the potential will be sum of two contributions. Here's only one. And you can take tropical points, and you can ask question, what do you get? And so in this case, you have three invariants, like lambda 1, lambda 2, lambda 3. In this case, you get two. I call it lambda, and the one somehow corresponds to this path you call mu. And in this case, you have only one, mu. And in this case, the theorem is that this is canonical basis of Lustig, per se, in the universal enveloping algebra parameterized by the set mu. Now, what mirror conjecture tells in this case? Actually, in this case, it's theorem. And this is theorem in the middle case, and this is basically the famous Giventhals quantum cohomology of the flag varieties. Let me explain why, and then I will stop. So the integral, let me write down the integral in this example. Again, so the picture is this. You have A, B, and the space of triples like that has canonical projection to the torus, which let me call it chi. And it also has another projection to another torus. And so what you do, you write down the following integral. Take integral of E2 minus the potential divided by the Planck constant. You multiply by the volume form. But now you use this projection, this kind of little different flavor of this map to Cartan group. And you insert here the character. You can write this as a T2 lambda, but really it's a kind of Mellin transport. It's character multiplied to that. So that's another integral, and it's known that this integral solves quantum So this integral, first of all, it depends on element of a torus H and a dual torus S. It's a character. So it's quantum connection for, if you consider equivariant quantum cohomology for the space G mod B. And this is Giventhal, and this is a topic which has lots of research. So let me just mention a few names here which are especially important. The number one is Giventhal, and then Giventhal and Kim. And this is 90-something. And then another people who took it in 21st century, this is Gerasimov, Lebedev, and Ablezin in a series of many papers. And also Constance Rich also treated. All of them, Giventhal is a case of GLN, or SLN. And this is, he said the whole somehow setup and proved it for SLN. And then for any group G, it's now proved, well established. And I just want to notice that, I mean, they don't write integral in this way. They don't have, this setup for the potential. But it turns out that my potential is just equal to their potential. If you do, for example, the Giventhal potentials, if you do calculations, some special nice coordinates which we introduced with Fock is just Giventhal's potential per se. But on the other hand, you see that you can play it with much more general setup, and you can put everything on surfaces. And so that's the end of the story, because I go over time already by 3 minutes.
Do you have any questions?
Yes?
So you mentioned affine flux. You probably need the points in this affine flux, right?
Let's call them principal affine space, yes.
But what if you took the actual affine flux?
Affine Grassmannian.
Yeah. So
This is the part, I mean, unfortunately, I didn't have time to talk about this. The proofs goes to the affine through the affine Grassmannian. Yes. So in order to prove this theorem, the most difficult thing you have to face, you have to go from something related to the group G to something related to group GL, which is Langland's dual group. Well, unfortunately, the only definition I know of the Langland's dual group, the definition, not the calculation, is the one proposed by Drinfeld and proved by many people, Mirkovic, Willan, Ginzburg, Lustig, and so on and so far, that the Langland's dual group is a category of perverse sheaves on the affine Grassmannian for the original group. And using this geometric static correspondence, actually, the theorem is proved. And if you use this theorem as given to you, the proof is just given by construction. It's in easy. I can explain it in 3 minutes, the construction, which says that you take a tropical point, and then you produce some infinite dimensional cell, which lives in the product of some copies of this affine Grassmannian. And then by geometric static correspondence, this cell corresponds to element of the tensor product of invariants. And this construction goes for any surface, any group G. It doesn't have to be this particular situation. So it's a very general construction which works for any surface. And my sense is that this is your linear defects. Okay.
What I'm asking is, what if the original group G it's a Cascudi group itself?
Oh, that's a different question and even more interesting question.
I'm asking.
Yeah, it's really not quite explored. So I mean, I assume that everything goes like that, but I mean the potential and so on are defined in so general terms that it's easy to define them. But then I didn't play with this yet. So presumably, it just goes.
A final question?
Yeah.
Well, then it just goes. What could be a better way to end this talk than to thank Sasha again?
Okay.